In this video, we will discuss invariant subspaces and eigenvectors and eigenvalues. This is our overview slide, which we'll spend about 5 minutes going over before we go over each topic in more detail and with more examples. We start with the idea of invariant subspaces. So suppose T is a linear operator over the vector space V. In other words, T is a linear map that goes from V and maps right back into V. A subspace U of V is called invariant under T if any vector U in the subspace U implies that T of U is in the subspace U. In other words, U is invariant if T restricted to U is an operator on U. Our first example then is if T is in the set of linear operators on V, show the following subspaces of V are invariant under T. First, we have the subspace consisting of only the zero vector. So we consider if this is our subspace is U equals the zero vector, then let's take the zero vector and apply T to it. So because T is linear, and we have a theorem that says linear maps take the zero vector to the zero vector, T of 0 is equal to 0, which is still in the subspace. And therefore, we say that this subspace consisting of only the zero vector is invariant under T. Our next example, suppose T is a linear operator on the space of polynomials over R. We're going to define T operating on a polynomial P is equal to the first derivative of P. Is P4, that is the space of polynomials of degree 4 or less, invariant under T? So here I have T of a representative element of P4, so our polynomial of degree 4 or less. When we take the first derivative, we get a polynomial of degree 3, which is less than 4, so it is still in P4, and therefore we say that this subspace, P4, is invariant under T. One of the simplest and most important examples of invariant subspaces concerns eigenvalues and eigenvectors. So we study eigenvectors, one of the simplest non-trivial invariant subspaces. So for eigenvalues, suppose T is in the space of linear maps L of V. The number lambda then in F is called an eigenvalue of T if there exists a vector V in V, the vector space V, not equal to 0, and T of V is equal to lambda V. That is, T of V takes V and it equals to a scalar multiple of V. So T scales V, it does not rotate or do any other type of transformation other than scaling. Then this vector V is called the eigenvector. Suppose T is in the set of linear transformations and lambda is in F and it's an eigenvalue of T, then the vector V in the vector space V is called an eigenvector of T corresponding to the eigenvalue lambda if V is not 0 and T of V is equal to lambda V. We have this theorem which gives us equivalent conditions to be an eigenvalue. Suppose V is finite dimensional and T is in the set of linear transformations or linear operators over V, and lambda is in F, then the following are equivalent. Lambda is an eigenvalue of T. B, T minus lambda I is not injective, T minus lambda I is not surjective, and T minus lambda I is not invertible. And this theorem is important as it gives us here this kind of formula here, which will help us find our eigenvectors, eigenvalues. The next thing I will do are two examples of eigenvectors, eigenvalues when your transformation is represented by a matrix A. Your book doesn't cover this in this chapter, but I feel like this is a good time to review. We have this next theorem that says eigenvectors are linearly independent. So let T be a linear operator on V, that is L of V. Suppose we have eigenvalues lambda 1, lambda 2 up to lambda m. They're distinct eigenvalues of T, and then we have the V1, V2, Vm are corresponding eigenvectors. Then the set V1, V2 up to Vm is linearly independent. Our last topic are the restriction operator and the quotient operator. So suppose T is a linear operator on V and U is a subspace of V that is invariant under T. Then the restriction operator, that is T over U in the space of linear operators on U, is defined as, and this is T restricted on U, takes a vector U and it equals T of U, for u and u. And because t is invariant, this t of u will stay in u. So we still have an operator. Then we have this quotient operator, t over u, in the space of linear operators of v over u. The quotient vu is defined by t over u operating on a vector u plus v, because remember it's operating on this quotient vu. That's equal to tv plus u for a vector v in the space v. That wraps up our overview, and we can come back over here, take a closer look at invariant subspaces. Suppose T is a linear operator over the vector space V. So in other words, T takes vectors in V and maps it back onto other vectors in V. A subspace U of V is called invariant under T if this vector U in the subspace U implies that TU is also in U. So in other words, if I take a subspace U here and I take a vector in U, TU then is going to map this vector back into something in the subspace U. So in other words, U is invariant if T restricted to U. So if we only consider the subspace U now, and we thought we ignored everything else outside of U. So this is T restricted just to U, is then an operator on U. In other words, it maps right back onto U. The way I personally like to think of invariant as is what happens in U stays in U. We will do some examples. Suppose T is a linear operator on V. Show that the following subspaces of V are invariant under T. Our first subspace is the space consisting of only the zero vector. What we need to consider now is what happens to these vectors in U when we apply the map T to the vectors. There's only one vector, so we're going to apply T to our one vector, 0. So we're looking at T of 0. And we have this theorem that says linear maps take 0 to 0, and because T is linear, that means T of 0 is equal to 0. And 0 is certainly an element of this subset U here, and therefore the 0 vector, that is a subspace that is invariant under T. Our next example is the entire vector space V. To determine if it is invariant, we need to know what happens to vectors in the vector space V when we apply T to them. Do they stay in the subspace V? So if V is a vector in the vector space V, then T of V is still in V because T is a linear operator on V. Remember, T maps from V to V. Since we're still in our subspace V, that means V is invariant under T. Our next example is the null of T. And remember, the null of T, if U is equal to the null of T, that means all of these vectors U all map to the 0 vector. So we need to consider what happens to the null of T as we apply our transformation. But we've sort of already determined that just by using the definition of null of T. So if U is in the null of T, then T of U is equal to 0, which is in the null of T. Our last example is the range of T. So first, let's remind ourselves what the definition of range of T is. So remember, T maps from V to V. So U is in the range of T if there exists some vector V in our domain such that T of V is equal to U. So in other words, if we take any U in the range of T and we apply our transformation T on that, by definition, because U is in the range of T, that means T of U is in the range of T, and therefore this subset is also invariant under T. Oh, I have one more example of an invariant subspace. So suppose T is the linear operator on the space of polynomials defined by T of a polynomial is equal to the first derivative of that polynomial. So is P4, the space of polynomials of degree 4 or less, invariant under T? We need to consider what will happen to a polynomial of degree 4 or less when we apply T to it. So here is my template of what a polynomial of degree 4 or less equals to. a constant a naught plus a1x plus a2x squared plus a3x cubed plus a4x4, these constants can be equal to 0, we're going to apply t to it. In other words, we're going to take its first derivative. The constant a naught goes away. Here our a1x, we're left with the constant a1. Here our 2 comes down and we get 2a2x. Here we get 3a3x squared. And finally we're going to get 4a4x to the 4th. And this polynomial is still a polynomial of degree 4 or less. And therefore, we would say that the space of polynomials of degree 4 or less, the subspace of the space of polynomials on R, is invariant under T. Looking at the simplest non-trivial invariant subspace is going to motivate our discussion of eigenvectors and eigenvalues. The example we'll take a look at is an invariant subspace with dimension 1. We will start by taking any vector v in a vector space V with our vector not equal to the 0 vector. We will then define U, our subspace, to be the set of all scalar multiples of V. That is, U is the set of vectors lambda V, where lambda is a scalar in our field. So this is equal to the span of the vector V. Since then U is spanned by a single vector, which is also linearly independent because it's only one vector, that means U is a subspace with one basis vector V, so it's a one-dimensional subspace of V. Now that we've established U as our subspace that is one-dimensional, if we further want to put the requirement that U is invariant under the operator T, then TV must be in U. That is, TV must be equal to a scalar multiple of V, because that's how we defined U. That is the space of scalar multiples of V. So this is the equation that must be satisfied for this subspace to be invariant. Conversely, if we have this equation as true, TV equals lambda V for some lambda in this field, then the span of V is a one-dimensional subspace. So we've defined our subspace again. And then by this equation, that subspace is invariant under T. So this is the equation then that becomes important if we're looking at an invariant subspace with dimension 1. This TV equals lambda V is exactly what we use then when we define our eigenvalues and eigenvectors. So suppose T is a linear operator on V, then a number lambda in F is called an eigenvalue of T if there exists a vector V in the vector space V not equal to 0 and TV equals lambda V. Lambda's corresponding eigenvector then, suppose T is a linear operator on V and lambda in F is an eigenvalue of T, any vector V in the vector space V is called an eigenvector of T corresponding to lambda if V is not 0 and TV equals lambda V. And from our previous example that motivated the eigenvector eigenvalue discussion, we have T has a one-dimensional invariant subspace if and only if T has an eigenvalue. And just to be extremely explicit, I have written our eigenvalue eigenvector equation, TV equals lambda V. I can subtract lambda V from both sides, so I have TV equals lambda V equals 0. Combining my lambda with T so I can factor out my V, I do need to multiply my lambda by the identity matrix, so I get T minus lambda I V equals 0. This is also our eigenvalue eigenvector equation that will allow us to solve for eigenvectors eigenvalues. And then we come to this theorem, equivalent conditions to be an eigenvalue. Suppose V is finite dimensional and T is in the space of linear operators and lambda is in F. Then the following are equivalent. Lambda is an eigenvalue of T minus lambda I is not injective, T minus lambda I is not surjective, and T minus lambda I is not invertible. I have the definition of the eigenvector and eigenvalue here for your reference, so we can do a proof of this last theorem, the three 4 equivalent conditions of lambda is an eigenvalue of t. To prove these 4 are equivalent, we're going to prove that A implies B, B implies C, C implies D, and then D implies A. We will start with A implies B. That is, we're going to start with assume lambda is an eigenvalue of T. We want to prove the statement B now. By the definition of eigenvalue, this statement here, that lambda is an eigenvalue of T, implies there exists a vector V in our vector space that's not equal to 0, such that TV is equal to lambda V. We can then subtract lambda V from both sides of the equation. Then to factor out the V, we have to multiply our lambda times I, and we get T minus lambda I V equals 0. And I just want to take a little bit closer look at this lambda I V. So our lambda I V, we can multiply lambda times, in this case, I just chose a 2 by 2, I was assuming we're in R2, identity matrix times V, and you can see then lambda will multiply by our matrix, and we get lambda 0, 0, lambda times V, which is equivalent to lambda times V1, V2, which is equal to lambda V. Looking at this matrix equation, we know that since V is an eigenvalue, and by definition our eigenvalues, our vector, is not equal to 0. So since V is not equal to 0, that means this matrix equation here, which I kind of have a demonstration of what it would look like if it were two-dimensional, has a non-trivial solution where V is not equal to 0. We have this theorem here about injectivity, since statement B is about injectivity, that says injectivity is equivalent to the null space equaling 0, the 0 vector. Now, since we have a non-trivial solution, that means there's a solution, or the null space has a non-zero vector in it. So the null space is not equal to 0, meaning now by this theorem that we do not have injectivity. That is, by this theorem and the fact that we have a non-trivial solution means that T minus lambda I is not injective. The next part of our proof will be B implies C. That is, we're going to assume B, T minus lambda I, is not injective, and we will prove that T minus lambda I is not surjective. But we had this theorem earlier for operators. Suppose V is finite dimensional and T is a linear operator on V. Then the following are equivalent. T is invertible, T is injective, T is surjective. So that means since T is not injective, we also know that T minus lambda I is not surjective, which makes C implies D, that T minus lambda I is not surjective implies T minus lambda I is not invertible, trivial, since to be invertible it must be surjective and injective. So we have T minus lambda I is not invertible. Finally, we have D implies A. So we're going to start with D. T minus lambda I is not invertible, and we want to prove lambda is an eigenvalue of T. So if T minus lambda I is not invertible, that means that T minus lambda I times a vector V equals 0 has non-trivial solutions for vector V. And we've seen that this equation is algebraically equivalent to TV equals lambda V. Since V is not equal to 0, it's non-trivial. That means that lambda is an eigenvalue of T. Our next example is to find the eigenvalues and their corresponding eigenvectors of a transformation represented by the matrix A, where A is the 2 by 2 matrix with column vectors 1, 1, and -1, 3. We start with our eigenvector equation. Our transformation T is now represented by A, so AV equals lambda V. We can move the lambda V over by subtracting from both sides. We get AV minus lambda V is equal to this. To combine the A and the lambda with the vector, we're going to multiply lambda by I. So A minus lambda IV will equal to 0. We solve this by using our matrix. Here's my A minus lambda IV, which is 1 minus lambda 1, minus 1, 3 minus lambda v, and again, it is equal to the 0 vector. By the invertible matrix theorem, which is not covered in this class, but covered in all first linear algebra classes, if you don't remember it, don't worry about it. The part we need to know is right here, that this matrix, or this system of equations, this matrix equation, has a non-zero solution v when the determinant of this matrix here is equal to 0. The determinant of a 2 by 2 matrix is notated with these bars, so this is determinant of A, B, C, D, and it's calculated by cross-multiplying AD and then subtracting the cross-multiplication BC. So it's AD minus BC. For our matrix here, then we cross-multiply. We get 1 minus lambda times 3 minus lambda minus 1 times 1. So that gives us a plus 1, and we set that equal to 0 because we want to know when the determinant is equal to 0. After some algebra, we find that lambda is equal to 2. So this is our one eigenvalue. That's repeated twice. To find our eigenvector associated with this eigenvalue, we plug in our eigenvalue into this equation and then solve for v. So what that looks like is, for lambda equals 2 then, plugging in a 2 for this lambda in our equation over here. I should change this from an x to a v. So here we have 1 minus 2, that gives us minus 1, our minus 1 here, and then 3 minus 2, that gives us a 1. We have our vector v, which we are trying to solve for, and it's equal to 0, 0. Again, this is just our eigenvector eigenvalue equation with our eigenvalue plugged in. Now we use our techniques from, chapter 1, where we solve the system of equations. I have the augmented matrix here. I row reduce to this matrix. So what I get is V2 is free, and V1 is equal to minus V2. So then my eigenvector looks like 1 for V2 and minus 1 for V1. I can now check my work by calculating A times V, so this is my matrix A, times my eigenvector V. When I multiply this out, I get minus 1 plus minus 1, which is minus 2 here. I have my minus 1 plus 3 is 2, and you can see that this is equal to my eigenvalue 2 times my eigenvector minus 1, 1. So I have AV is equal to lambda V. You can also verify that any scalar multiple of V will also work in the eigenvector eigenvalue equation. I have this note here, which shouldn't be a surprise because this is how we set up our eigenvector eigenvalue equation. It was to be the simplest example of an invariant subspace. So eigenvectors are scaled and not rotated by the transformation. In our example, you can see this negative 1, 1 vector was then scaled, so it's twice as long here. But you can see that minus 1, 1 points in the same direction as minus 2, 2. It has not been rotated. And there is one other comment I'm going to make, is our matrices are always going to be square because we're talking about linear operators. Since T maps from V to V, we will always have square matrices. My next example is to find the eigenvalues and corresponding eigenvectors of a transformation T represented by a 3 by 3 matrix A, whose column vectors are 1, 0, negative 2, 1, 3, 1, 1, 3, 1. And for this problem, I have the formula for determinant of a 3 by 3 matrix up here. So we have the 3 by 3 matrix with column vectors A11, A21, A31, and then the second column vector is A12, A22, A32, and our last column vector is A13, A23, and A33. To find the determinant, we're going to expand along the top row. So first we're going to take the first element of our top row, that's A11. I'm going to cross out the rest of the row and column that A11 belong to, and I'm going to multiply my A11 by the remaining matrix determinant. So that's A22, A32, A23, A33. I'm then going to go to my next element on the top row, cross out the rest of the top row and the column that A12 belongs to. The signs on my determinant will alternate, so now I'm going to have minus A12, and then I take the determinant of what's left. That's the A21, A31, A23, and A33. Finally, I take my last element on my top row, cross out the rest of the row and column that A13 is in. I'm going to add that to A13 times the determinant of this 2 by 2 matrix here, A21, A31, A22, A32. And then finally, now that I have everything as a 2 by 2 matrix, I copy my formula for the 2 by 2 matrix from our previous slide. We just cross multiply AD minus BC. I'm going to pick up here in this problem where I'm looking at my matrix A minus lambda I. So essentially what I'm going to do is subtract lambda on the diagonal. So I'm going to have 1 minus lambda, 0 minus 2 for my first column. I'm going to have 1, and then 3 minus lambda, 1 for my second column, and my final column will be 1, 3, 1 minus lambda. And you recall this equation here has non-trivial solution when the determinant of this t minus lambda I is equal to 0. So I'm going to take the determinant. I start by expanding across the top row. I have my first element, 1 minus lambda. I cross out the rest of the row and column that this element 1 minus lambda is in, the same row, same column. And I'm left with this matrix here, 3 minus lambda, 1, and then the next column, 3, 1 minus lambda. Next, I take my next row, I cross out all the elements in that row and in that column. Remember the determinant, these signs alternate, so this is minus 1 times the determinant that's left. That's 0 minus 2 and 3, 1 minus lambda. Finally, I'm going to expand across the last row. So I take my last element of my first row and I cross out the rest of the first row and the rest of the column that belongs in. So I have my plus 1, and then I have 0 minus 2 and 3 minus lambda, 1. Now I need to take the determinant of my 2 by 2, which is done with this formula. So I still have my 1 minus lambda, then I have my 3 minus lambda times 1 minus lambda here, minus 3. I have my minus 1, 0 times 1 minus lambda, 0, minus the 3 minus 2, so I get a positive 6. Over here, I have a 1 times my 0 times 1 is 0, and then my minus 2, 3 minus lambda, so that becomes plus 2, 3 minus lambda. I feel like the worst part of this process is actually doing the algebra, but it algebraically simplifies to minus lambda, lambda minus 2, and lambda minus 3. We haven't really gone over this in the main part of our video, but we talked about this in our overview. So I'm just going to pop this up now. So suppose V is finite dimensional, then each operator, that is each transformation, in this case we have a matrix to represent a transformation on V, has at most dimension V distinct eigenvectors. Here we're in 3 space, we're in R3, so we can expect at most 3 distinct eigenvalues. Here we have exactly 3. The reason why we say at most is it's possible, like in our last example, we could have something of this form, lambda minus 2, in which case lambda equals 2 is our one distinct eigenvalue. It's just that it's repeated twice. Setting this equal to 0 then, we get lambda equals 0, lambda equals 2, and lambda equals 3 as our eigenvalues. So I am going to show you lambda equals 2. I plug in lambda equals 2 into my A minus lambda I equation. So it's just A with minus lambda across the diagonal. So we have 1 minus 2, which is negative 1. Then we have 0, negative 2. We have our 1, and then we have our 3 minus our lambda, which is 2. So 3 minus 2 is 1, 1. And then we have 1, 1, and then we have 1 minus 2, which is minus 1, times our vector v, and we set that equal to 0. We're looking to see when this equation has a non-trivial solution for V. We then have the augmented matrix here, which is column vectors -1, 0, -2, 1, 1, 1, 1, 3, -1, 0, 0, 0. It row reduces to the matrix with column vectors 1, 0, 0, 0, 1, 0, 2, 3, 0, and 0, 0, 0. This last row means V3 can be considered free. Here we have V2 is equal to minus 3 V3, and here we have V1 is equal to minus 2 V3, which means our eigenvector associated with the lambda equals 2 eigenvalue is minus 2, minus 3, 1. You can check your answer by having our matrix A multiplied by our eigenvector, and that should give you the same thing as our eigenvalue times our eigenvector, and it does check out. There are two more eigenvectors, lambda equals 0 and lambda equals 3, but I'll let you work those out on your own, and you do have a way of checking your work. I have another example. This one's from your book. Suppose T is a linear operator over F2. So T takes vectors from F2 to F2, and we define it as T of WZ, so this implies that we're in the complex plane, potentially, is equal to minus Z W. And I say W and Z, those normally denote complex numbers, whereas X and Y normally denote real numbers. So A, find the eigenvalues if F is equal to real, and then B, find the eigenvalues if F is equal to C, the complex field. So this transformation T of WZ equals minus ZW in R2 represents a rotation. For example, let's just take W equals 1 and Z equals 2. That would mean we have minus 2, 1. So we start off with this vector 1, 2, and then we rotate it to minus 2, 1. And since eigenvectors are only scaled and not rotated, we will say that this transformation has no eigenvalues if our field is equal to the field of real numbers. We can now look at B, where we consider T of WZ equals minus ZW, where W and Z are complex numbers. If we do have an eigenvalue for this transformation, then TWZ is going to equal to lambda WZ. Setting these two equal, that will imply that our negative Z is equal to lambda W, and W is equal to lambda Z. Plugging in this W, lambda Z, into this equation, we get minus Z is equal to lambda times lambda Z, which means minus Z is equal to lambda squared Z, which gives us lambda is equal to plus or minus I. And here's the problem that we have when we try to do this problem in the real numbers. We don't have a purely real solution. We only have this imaginary solution. We have two eigenvalues now, lambda equals I and lambda equals minus I. Let's consider lambda equals I first. Looking at this equation then, we have minus Z equals IW. Or we could use this equation, W is equal to IZ. They're really the same equation, that's all this is. But essentially what we have then is that our eigenvector then is equal to W, and Z is equal to minus IW. So this is our eigenvector associated with our first eigenvalue, lambda equals I. For our second eigenvalue, lambda equals minus I, plugging in here we get minus Z equals minus IW, or plugging here we get W equals minus IZ. Essentially both of these are saying that the same thing, that when we have W, then Z is equal to positive IW. So this is our eigenvector associated with our second eigenvalue. I would like to show you this sort of similar graphical representation of this, but the difficulty comes from the fact that each of these complex numbers, the complex numbers Z and W, requires a plane to represent. So because Z has a real and an imaginary part, usually to represent a complex number, we graph the real part on the x-axis and the imaginary part on the y-axis. So this would take a a plane to represent, and this would take a plane to represent. When we graph it in R2, a real number vector, here to do a complex number vector, we would need something kind of more in 4 space. It's not so much the mapping, because we could do a mapping from a complex number to a complex number. It's the complex, the F2, the complex vector to complex vector mapping that would give us problems and is beyond the scope of this class. Now that we've done some examples of these eigenvectors, eigenvalues, we're going to look at this theorem that says that eigenvectors are linearly independent. Again, I've left my definition of eigenvectors and eigenvalues in the eigenvector eigenvalue equation here for your reference. And our theorem says let T be a linear operator on V, that is L of V. Suppose then lambda 1, lambda 2 up to lambda m are distinct eigenvalues of T. And this is important. They're distinct. They're not repeated eigenvalues. And V1, V2, Vm are corresponding eigenvectors. Then V1, V2, Vm is a linearly independent set. And we're going to do this proof by contradiction. That is, we're going to suppose the eigenvectors V1, V2 up to Vm are linearly dependent. That means there exists some vector in V1, V2, Vm that is linearly dependent on the others. We're going to let k be the smallest integer such that V sub k is in the span of the previous k minus 1 vectors. This statement here for linearly dependent vectors was proven in an earlier video. And if you're good with this statement, I would say plow on ahead, skip what I'm going to say in blue here. But if you are like me, you haven't seen that proof in a while, and it sort of bothers you because this k sort of depends on the order that these vectors are listed, and who knows what order people are going to list these vectors, then this kind of aside is for you. So let's say we have these 3 vectors, 1, 1, 1, 0, 0, 1, and 3, 2. This is a set of linearly dependent vectors because this 3, 2 can be written as a linear combination of the 1, 1 and 1, 0. And in fact, this 3, 2 can be written as a linear combination of all the previous vectors in this list. In other words, it can be written as 2 times 1, 1 plus 1 times 1, 0 plus 0 times 0, 1. So as far as this statement is concerned, k is equal to 4 because that's the 4th vector can be written as a linear combination of the previous 3. Now, if we change the order of these vectors, so the 3, 2 and the 1, 0 changes places, so we have 1, 1, 3, 2, now we have 0, 1 and 1, 0, k is still going to be equal to 4 because now this 1, 0 can be written as a linear combination of the previous 3. In particular, this 1, 0 over here is equal to 3, 2, and then we just move this vector over to the other side, minus 2 times 1, 1. And then, of course, you can add a 0 here. So k is still equal to 4 in this case. This vector is a linear combination of the 3 previous vectors. I'm going to move this case aside now when we rearranged these vectors. And now I want to rearrange the order of these 2 vectors where one of these vectors has the 0 as our coefficient. If our set is now 1, 1, 1, 0, 3, 2, 0, 1, now since 3, 2 can be written as a linear combination of the previous 2 vectors as we did over here, our k is equal to 3. So it is true, depending on the order of vectors, you'll have different k's. But as long as they're linearly dependent, you're always going to have some smallest k that can be written or is in the span of the previous k minus 1 vectors. And at the very worst, because they're linearly independent, k is equal to m. Okay, no pun intended. We're back where we are here. Let k be the smallest integer such that v sub k is in the span of the previous k minus 1 vectors. When we take the transformation of v of k, that's the transformation. We can now write v of k as a linear combination of the previous k minus 1 vectors. And now since t is linear, we can factor out our constants and we can also separate out our summations. But since v1, v2 up to vk, and actually also as vm, they're all eigenvectors. So now we can write this as lambda k vk, and all of these have our t of v1 now becomes lambda 1 v1, t of v2 becomes lambda 2 of v2, all the way up to k minus 1. We can now take our vk, written as our linear combination of the previous k minus 1 vectors. We can multiply both sides of this equation now by lambda k. Oops, let me move this down. And actually, just to get this out of the way, I'm going to move this up here so that these two equations can be closer, because I'm going to subtract this equation from this equation here, which will give me, and let me just put a little subtraction sign so we know what's going on. On this side, we have vk times lambda k, so subtracting, we get 0. Over here, I should have lined these up a little better. Maybe I can do a better job. We have the v1, we have an a1, and then we have lambda 1 minus lambda k. For v2, we have a2, and then we have lambda 2 minus lambda k, all the way down to k minus 1. Then we have our vk minus 1, our ak minus 1, lambda k minus 1 minus lambda k. But remember, we chose v sub k to be the smallest index that is linearly dependent, which means this list, which is the previous k minus 1, must be independent, which means there's the solution where all the a sub i's are equal to 0 because they are independent. But that would mean our v sub k is equal to 0, which contradicts our hypothesis that v sub k is an eigenvector. Remember, eigenvectors are not equal to 0. Since we have this contradiction, that must mean that our assumption here was incorrect, so our m eigenvectors must be linearly independent. I'm going to mention the importance of this theorem as if you are in an m-dimensional vector space, then m linearly independent vectors is a basis. And we have our corollary, the number of eigenvalues. Suppose v is finite dimensional, then each operator on v has at most dimension v distinct eigenvalues. Our last topic is going to be on the restriction operator and the quotient operator. I've kept my eigenvalue definition here, and we're going to start with our restriction operator and quotient operator. Suppose T is a linear operator on V, and U is a subspace of V, and it's invariant under T. So T is a linear operator on V, U is a subset or subspace in particular of V, and for any element or vector U in the subspace U, T of U is equal to, I'm going to draw a picture of this. So we said T is a linear operator on V, so it maps from V to V. And U is a subspace of V that is invariant under T. So I'm just going to draw U in blue. It's this little subspace of T. And whenever T maps from U, it maps right back into U. And in fact, it'll take a vector U and map it to a lambda U. Oops, I put lambda V, lambda U. The restriction operator, which we denote with this T slash U, is a linear operator in U, and it's defined as T slash U operating on a vector U is equal to T of U for all vectors U and U. In other words, instead of now considering T on the whole vector space V, we're going to restrict our domain just to U and consider what happens. Since we have this U is this eigenvector eigenvalue relationship, when we map a vector U in U by T, we're going to get lambda U. Since U is a subspace, lambda U is still in U because subspaces are closed under scalar multiplication. So in other words, when we restrict the domain of T to U, we still have a linear operator, and we call this new linear operator the restriction operator, T restricted to U. We have this note T with its domain restricted to U is a mapping to U, which makes it a linear operator. The next operator we will consider is the quotient operator T over U, which is a linear operator over V over U. And it's defined by T over U, taking an element from V over U, which is V plus U, or looks like V plus U, is equal to TV plus U for a vector V in the vector space V. And let's just do a really quick review of this V over U. Suppose V is a vector in a vector space V and U is a subspace of V, then V plus U, that's what this is, these are elements of V over U, is the subset of V defined by V plus U is equal to V plus U for all vectors U in V. So in other words, this was our picture. If we have a subspace U here and we want to add a single vector to it, then what we're doing is we're raising this point by our vector V. Now if we do this for every point in our subspace, what we end up doing is raising our entire subspace by this vector. We then define an affine subset of V is a subset of V of this form, V plus U for some V in the vector space V and U some subspace of V. And then the affine subset we said was parallel to U because they're all, U is basically offset everywhere by the same vector V. And then we define the quotient space, this V over U. Suppose U is a subspace of V, then the quotient space V over U is a subset of all affine subsets of V parallel to U. Here are our affine subsets. So here's one displacement of U by a vector V. A different vector V will give us this plane that's parallel to U but offset. Another vector V will give us this yellow plane. Now we have the quotient operator and it's on the space, this quotient space VU. So it operates on this space here. So it'll take one of these V plus U's, one of these planes. It'll map it to TV. Remember, TV is has this eigenvector eigenvalue relationship plus U. So in other words, first what we're going to do before now we add this to U, we're going to multiply our V by the eigenvalue. So the picture is, if this was our U, this was our original vector V. So our first affine subset was this blue space here. But now we're going to do the quotient operator on this V plus U. And what we're going to do is come back to this V, take the transformation, which by the way is an eigenvector, eigenvalue, linear, this invariant transformation. So it scales V by some scalar multiple, and then we're going to take the affine set here. So essentially, it kind of boosts up this affine subset by our eigenvalue. The value of the restriction operator and the quotient operator is it allows us to study T on a subspace U in a smaller dimension than V. So suppose T is a linear operator in a finite dimensional space V, and U is an invariant subspace of V, invariant under a transformation T, with U not equal to just the zero vector and also U not equal to the entire space V, then in some sense we can learn about T by studying the restriction of T on U and the quotient of T of U, each of which is an operator on a vector space with smaller dimensions than V. We have this example for restriction operator and quotient operator. Define an operator T on F2 by T of xy equals y0. Let U be the subspace x0 for x in F. A, show that U is invariant under T, and then show that T restricted to U is the zero operator on U. B, show that the quotient operator T over U is the zero operator on F2 over U. My notes here, T is a linear operator over F2, T of xy equals y0. And here, well, we're in the F over some field F. We don't know if it's the real numbers. If it were the real numbers, then we would be talking about the plane where y is equal to 0. But U is the subspace restricted where our second coordinate is equal to 0. So to show U is invariant under T, we need to know what happens to a vector u in the subspace u. So let's look at T of u. If u is in the subspace u, then u has the form x0. So we're looking at T of x0. Applying our transformation then on x0, we're going to get 0, 0. And 0, 0 still is in the form of the subspace u, so therefore it stays in u, and u is invariant under T. And we get the second half right here. Since T restricted to u, which is exactly what this shows us, for any u in the subspace, T of u is going to equal to 0, 0. So in other words, T restricted to u is the 0 operator. It maps everything to 0. Our next problem is to consider the quotient vector T over u and show it is the 0 operator on F2. So we want to know what T over u does to vectors in F2. For that, we're going to consider our vector v is equal to v1, v2, and that's a vector in F2. Looking at T over u of v plus u is T over u. I'm going to substitute for v, v1, v2 plus u. Using our definition of the quotient operator, T over u of v plus u is equal to tv plus u. So I'm going to have T of v1, v2 plus u. Applying now our transformation to v1, v2, where is our transformation over here? That'll give us v2, 0 plus u. But since v2, 0 is an element of the subspace u, we can just say that this is equal to u, because this added to the subspace it's contained in is simply the subspace. So in other words, this quotient operator T of u will take our vector plus a subspace u, and it gives us back our subspace. So T of u is essentially the 0 operator. I am now going to do a quick review of what we have covered in this video. We first talked about invariant subspaces. Suppose T is a linear operator over vector space V. A subspace U of V is called invariant under T if for all vectors in U implies that T of U is still in U. In other words, U is invariant if T restricted to U is an operator on U. And we did several examples of invariant spaces. We went on to one of the simplest non-trivial invariant subspaces. They involve eigenvectors and eigenvalues. So an eigenvalue, suppose T is a linear operator on V, a number lambda in F is called an eigenvalue of T if there exists a vector, the eigenvector, in V not equal to 0, such that T of V equals lambda V. And we kind of just defined the corresponding eigenvector. We have equivalent conditions to be an eigenvalue. Suppose V is finite dimensional, T is a linear operator on V, and lambda is in F. Then the following are equivalent. Lambda is an eigenvalue of T. T minus lambda I is not injective. T minus lambda I is not surjective. And T minus lambda I is not invertible. We did some examples of finding eigenvectors and eigenvalues when the transformation is represented by a matrix, plus a couple of other examples from your book. We also have this important theorem here that vectors, eigenvectors, are linearly independent. And that becomes important because if you have the right number of linearly independent vectors, you have a basis. Finally, we talked about the restriction operator and the quotient operator. So suppose T is a linear operator on V and U is a subspace of V invariant under a transformation T. We can then talk about the restriction operator, T restricted to U, which is essentially the linear operator when we restrict T's domain to be the subspace U. Next, we talked about the quotient operator, and it operates on the quotient space V over U. So the quotient operator T over U on V plus U is equal to T on the vector V plus the subspace U. And that's it for this video. Thank you for watching.